Hello everyone, welcome back to my channel. If you're new here, on this channel I'll be doing IGCSE physics related content like past papers, topic questions, and overall revision. So if you're interested, make sure to like and subscribe for more upcoming content. So today I will be doing IGCSE Physics paper 42 for the May June 2023 series. So let's start with the first question. Number 1. A. Figure 1.1 shows a helicopter which is stationary at height 1,500 meters above the ground. The first question asks, state two conditions necessary for the helicopter to remain in equilibrium. So for an object to be in equilibrium, the first condition is that there should be no resultant force. So the answer should be no resultant force. And for the next one, there should be no resultant moment. So those are the two conditions needed for an object to be in equilibrium. So we write no resultant moment. That's going to be the answer. Part 2. The mass of the helicopter is 3,200 kilograms. Calculate the change in gravitational potential energy of the helicopter. So to calculate the gravitational potential energy, the formula is mass times gravity times height. So the mass is given, which is 3,200 times the gravity, we can just take it as 10, and the height is 1,500 meters. So we multiply all these and we should get, we'll be getting 4.7 times 10 to the power of 7 joules. We can write it as standard form over here because it's easier. Our answer is going to be 4.7 times 10 to the power of 7. The next question. B. Figure 1.2 shows a vertical speed time graph for a parachutist who jumps from a stationary hot air balloon. The parachutist jumps from the balloon at time 0 and reaches the ground at B. The point A indicates when the parachute opens. So this point over here shows that when the parachute opened, so the speed decreased. And on figure 1.2, label the point on the graph where the acceleration is 0 with 1, negative with 2, and decreasing with 3. So as we all know, if the acceleration is 0 and if it's a speed time graph, that means it's going to be a straight horizontal line. So we can label this one 1, or it could also be this one. And negative, so the acceleration is negative when the speed is decreasing. So it's this section over here. So we can label this 2, and decreasing. So the acceleration is decreasing on this section of the graph because of the curve, and this we can label 3. If the graph was going something like this, that means the acceleration would be increasing. But since it's going this way, the acceleration is going to be decreasing. Next question. 2. Explain in terms of forces the changes in motion which occur when a parachutist leaves the hot air balloon until point A. So we know that point A is when the parachute opens. So what happens when the parachutist leaves the hot air balloon? First, we have the person, and then the person will be going downwards. So when the person is going downwards, the speed is increasing. So if the speed is increasing, that means the weight of the object is greater. So the weight is going to be increasing. So the weight is greater than the resistance force, which is acting upwards, or the air resistance. But as the speed is increasing downwards, that means the air resistance would also increase. So there would be more resistance upwards. So which brings a change in speed. So the speed decreases after some time. So there would be less acceleration after a while, and then after that the speed would be equals to, so the speed would be equals to the air resistance. So once that happens, that means there is no resultant force. So the resultant force would be equals to 0. So that means the person would be moving at a constant speed. So we can write this down as the speed. First, there's a resultant force of downwards, like the weight. So the weight is greater than the resistance force. Then, as the speed increases, the air resistance also increases. And then after that, the resultant force would be 0 because those two upward and downward force match. So the resultant force would be 0. Force will become 0. Then the object will move at a constant speed, or the person would move at a constant speed. So the person moves at a constant speed. So that's going to be our final answer. Let's move to number 2. A student catches a cricket ball. The speed of the ball immediately before it's caught is 18 meters per second. The mass of the cricket ball is 160 grams. Calculate the kinetic energy stored in the cricket ball immediately before it's caught. So we know that kinetic energy is the same as half of mass times velocity squared. So we're given the mass, we're given the velocity. So this should be easy. But then we have to convert the mass 160 grams into kilograms. So we should do 160 over 1000. So this two zeros cancel. So 16 over 100 becomes 0.16. So this is going to be the mass in kilograms. So we multiply this by 18 squared. So 18 squared is going to be 324. And then we divide all this by 2. So this should give us a final answer of 25.92. We can round it to 25.9. And then joules as the unit for kinetic energy. B. It takes 0.12 seconds to catch the ball and bring it to rest. Calculate the average force exerted on the ball. So to calculate the average force, what we do is we use the force formula, which is force is equals to mass times acceleration. But then we don't have the acceleration here, so we have to calculate it. From the previous part, we know that the speed is 18, and then we have the time given, which is 0.12. So to find the acceleration, we divide the speed by the time. So 18 over 0.12. And that's how we find the acceleration. So 18 over 0.12, that would give us 150. So acceleration is 150 times, and then the mass we're given, which is 0.16 kilogram. So when we multiply those two together, we'd get 24 as the average force. 24 newtons. Next question. As the student catches the ball, she moves her hand backwards. Explain the effect of this action on the student's hand. So if the student moves her hand backwards, that means there would be more contact between the ball and the student's hand, more time of contact, so it would hurt less. You can just basically write that. So we can say there would be longer contact, so it would hurt less. Hurts less. That's going to be our answer. Question number 3. A. Figure 3.1 shows a person moving across an ice-covered pond to reach a ball on the ice. So here's the ball, and here's the person crawling to reach the ball. Explain why this way of moving across the ice is safer than walking. Use your understanding of pressure in your answer. So basically what happens is when the person is like crawling or laying flat on the ice, there would be more surface area in contact with the ice. So we know that pressure is equals to force over area. So if area increases, that means pressure decreases. But if the person is walking, that means it's only the feet that are going to be in contact with the surface. So that means the area is going to be really small. So the pressure is going to increase. So if the pressure is increased, that means the person could, sink into the ice or break through the ice. So when we write that, we can say there would be larger surface, larger area in contact. So larger area in contact. And then for our next point, and since pressure is equals to force over area, since pressure is equals to force over area, the pressure is less or really low. So the ice is less likely to crack. It's less likely to crack. That's going to be our answer. Part B. Figure 3.2 shows on a side view of a pond with a layer of ice floating freely on the water. So this is the ice layer over here. And then the surface area of the pond is 5 meters cubed. The mass of the ice is 690 kilograms. The density of the water is 1000 kilograms per meter cubed. Point X is 0.45 below the ice. So point X over here is 0.5 meters below the ice. Calculate the pressure at point X due to the ice and the water. So to do this question, we have two pressures we have to find. First, we have to find the pressure due to the ice, and we have to find the pressure due to the water. So pressure for solids is equals to force over area. So to find the force, we're given the mass, so we multiply the mass, 690, by 10. So that would give us 6,900, which is the force or the weight acting downwards. So we have 6,900, and the area is 5. And when we calculate that, we get 1,380. So right, 1,380. So that's the pressure due to the ice. And to find the pressure due to the water, the formula is pressure is equals to density times gravity times height. So the density is 1000 and the gravity is 10 and the height is going to be 0.45. And then what we get is 4,500. Now we just add this to 4,500 plus 1,380, and that would give us 5,880 pascals. Don't forget the units. And that's how we're going to get those 4 marks. Number 4. A. The temperature of a fixed mass of gas at a constant volume is decreased. State and explain in terms of particles how the pressure of the gas changes. So what happens when the temperature is decreased but then the volume is constant? So what happens is there would be kinetic energy is going to be decreased. So the particles would move slower, and due to their slow movement, they're going to collide less frequently, and when they collide with the walls, they're going to collide with smaller force. So when we write this, we can write that the kinetic energy is decreased. So kinetic energy decreases. So the pressure also decreases. So it decreases. Then the particles would collide less frequently and with less force. Particles collide less frequently with less force. Less force. That's going to be our answer. The next question. State the value of absolute zero in degrees Celsius. So absolute zero is where it's going to be 0 kelvins. So 0 kelvins is equals to negative 273 degrees Celsius. That's going to be absolute zero. Explain what is meant by the term absolute zero. Refer to particles in your answer. So absolute zero is the temperature at which it's the lowest possible temperature. So absolute zero is the lowest possible temperature. And it's where the particles have the least kinetic energy. Where particles have the least kinetic energy. Kinetic energy. That's going to be our answer. And the value is equal to 0 kelvins or negative 273 degrees Celsius. Part C. Cylinder 1 contains 350 centimeter cubed of gas at pressure of 9 times 10 to the power 4 pascals. The gas is transferred to cylinder 2 and the pressure is increased to 1.6 times 10 to the power 5 pascals. The temperature remains constant. Calculate the volume of cylinder 2. So to find the volume of cylinder 2, we use the formula P1 times V1 is equals to P1 times P2 times V2. So we have P1 as 9,000 and V1 as 350, and this should be equals to 16,000 times V2, which we do not know. So to find V2, we divide 16,000 from both sides. Sorry about my handwriting, it's really hard to write using a mouse. $16,000, so we can cancel the 3 zeros. So it's going to be 9 times 350 divided by 16, which would give us 196.875. We can just round that to 197 centimeter cubed. Number 5. A. Figure 5.1 shows an electric heater used to heat a room. The dimensions of the room are 4.5 meters times 6.1 times 2.4. The density of air is 1.2 kilogram per meter cubed. Show that the mass of the air in the room is 79 kilograms. So we know that density is equals to mass over volume. We have the density, which is 1.2, and the mass will remain unknown, and the volume is 4.5 times 6.1 times 2.4. That would give us 65.88. And then we cross multiply to find the mass. So the mass would be equals to 65.88 times 1.2, which gives us 79. This 79 is equals to the one given, so that means it's correct. And we've proved it. Part 2. The power of a heater is 1100 watts. The specific heat capacity of air is 1000 joules per kilogram. Calculate the time taken to increase the temperature of the air in the room from 16 degrees Celsius to 20 degrees Celsius. And it has 4 marks. So first we have to find the energy. And the formula is Q is equals to mass times specific heat capacity times change in temperature. So the energy, mass, we have found that, which is 79 kilograms in the previous question, times specific capacity, which is 1000, times the change in temperature, so 20 degrees Celsius minus 16, which is equals to 4. So our energy is going to be 4 times 1000 times 79, which gives us 316,000. And then we know that power is the same as energy transfer over time. So time is going to be power times time is going to be energy transferred. So we divide power from both sides. We're going to get time is equals to energy transferred over power. So energy transferred is 316,000, and then the power is going to be 1100. We can cancel 2 zeros, and then our answer is going to be 287. So 287 seconds. That's our final answer. Suggest one reason why the time calculated in A part 2 is the minimum time needed to increase the temperature of the air in the room from 60 degrees Celsius to 20 degrees Celsius. So for this, we can write that thermal energy is transferred to other places, like to the furnitures in the house or to the windows. So thermal energy is transferred to the furnitures, the windows, and the doors. I'm just going to write furnitures, and it should be okay. The next question. Figure 2.1 shows a cross-section of a double-glazed window in a room. State the main methods of thermal energy transfer from the room to outside which are reduced by this type of window. So the main methods, methods show us that we have to write 2 methods. So the method for thermal energy transfer are either conduction, convection, or radiation. Now it's obviously, one of them is obviously conduction. So we can write conduction because it's a solid. And the next one is going to be convection because this is a narrow air gap. So that means there's air particles over here. So because of the air particles, heat energy will also transfer through the air particles. So it's going to be convection too. It's not radiation because there is a medium, and radiation is transfer of heat energy without any medium. Number 6. Two types of seismic waves are P waves and S waves. State the types of wave that P waves and S waves can be modeled as. So there are two types of waves, and that are longitudinal and transverse waves. So P waves are longitudinal waves. So P waves are longitudinal, and S waves are going to be transverse waves. Transverse. Part B. The velocity of a P wave in Earth's solid crust is 7.2 kilometers per second, and its frequency is 4.5 hertz. Calculate the wavelengths of this P waves. So first we have to convert the 7.2 kilometers per second into meters per second. So that would be 7,200 meters per second. We just multiplied by 1000. And then we have 4.5 hertz. So speed is the same as frequency times the wavelengths. This is the sign of wavelengths. So we divide both sides by the frequency to find the wavelength. So velocity over frequency, so 7,200 over 4.5. So it's going to be 1,600 meters. Number 7. Figure 7.1 shows a container of oil. A ray of light shines on the surface of the oil. The refractive index of the oil is 1.47. On figure 7.1, draw the normal at the point where the ray enters the oil. So the normal line should always be at 90 degrees to the surface. So we just write a straight perpendicular line over here. So that's the normal line. We can also extend it down. So that's going to be our normal line. The angle x is 56 degrees. So if this is 56 degrees, that means this part over here is going to be 90 minus 56 degrees. And it's going to be 34. So this is the angle of incidence, is also known as I. Calculate the value of the angle of refraction. So we know that the refractive index, also known as N, is equals to sine of I over sine of R. So we have the refractive index and I. So refractive index is 1.47. And then sine of I is going to be sine of 1.47. Sorry, sine of 34 degrees over sine of R. So we can cross multiply. So this gives us 1.47 times sine R is equals to sine 34. So we divide both sides by 1.47 and 1.47. So sine 34 divided by 1.47 is going to be 0.38. 0.38. So this value gives us sine r. Sine r is going to be 0.38. So we can multiply this by the inverse of sine, so times sine inverse, and this also multiplied by inverse of sine. We can also do that on the calculator, and it would give us 22.35 degrees. We can just write it as 22 degrees. So angle of refraction is going to be 22 degrees. State the approximate speed of light in air. So that's basically, it's always it's always going to be 3.0 times 10 to the power of 8 meters per second. So it's going to be 3 times 10 to the power of 8 meters per second. That's going to be our answer. The next question, D. Calculate the speed of light in the oil. Give your answer to 3 significant figures. So we're given the refractive index, which is 1.47 from the previous question. And what else we're given? So the refractive index, the other formula, is going to be the speed of light in air. So the speed of light in air over the speed of light in other medium. So in this case, in the oil, the speed of the light in the oil. So we know that speed of light in air is going to be 3 times 10 to the power of 8 over, let's just call this V. So now we have to rearrange the formula to find V. So 1.47 V is equals to 3 times 10 to the power of 8. So we can divide both sides by 1.47. And then we should get 2.04 times 10 to the power of 8. Or times 10 to the power of 8 meters per second, of course. That's going to be our answer. Number 8. A. State what's meant by a magnetic field. A magnetic field is a region where a magnetic pole experiences a force. So a region where a magnetic pole experiences a force. A force. That's going to be the answer. Define the direction of a magnetic field. So we know that the direction of a magnetic field is always going to be from the North Pole to the South Pole. So we can just write it as the direction of a force on the North Pole. Let's write direction of a force from the North Pole. Part B. Figure 8.1 shows a negatively charged metal sphere. On figure 8.1, draw 4 lines to show the electric field and its direction. So electric field is basically the direction of positive charge, and So over here we know that the sphere is negatively charged, so positive charges are going to be attracted towards this sphere. So what we should do is draw 4 lines first, and they should be equally spaced out. So these are the 4 lines, and then their directions should be towards the sphere because it shows the direction of positive charge, and positive charges are attracted to negative charge. Part C. Figure 8.2 shows a circuit. The 3 cells are identical and have 0 resistance. So these 3 cells have 0 resistance. The resistors R1, R2, and R3 are also identical. The reading on the voltmeter is 6 volts. Over here, this is 6 volts. When the diode is conducting, it has 0 resistance and 0 potential difference across it. Determine the EMF of one cell. So if 3 of the cells give us 6 volts, that means we can just do 6 divided by 2 and 6 divided by 3, and you just get 2, because if 6 volts comes from 3 cells, that means one cell is going to give us 2 volts. So our answer is going to be 2 volts. Oops, I don't know what that was. 2 volts. Part 2. Determine the ratio of the potential difference across R2 to the potential difference across R3. So the ratio is going to be 1 to 2. So R3 is going to get twice the potential difference of R2, because over here we have the diode, and the diode is directing the current towards R3. So R1 is not getting any current. So the direction of current is going to be moving downwards, and then it goes to the diode, and then it goes back again. And R3 is only getting the once. The current's going to the R2 only once. So this gets it once, this gets it twice. So the answer is going to be 1 to 2. Part 3. All the cells are reversed. State and explain the change in current in R. So if all the cells are reversed, that means the current is going to change direction. So first, the direction of the current was this side. If we're talking about conventional current, it was anti-clockwise. Now if the cells are reversed, that means the direction of the current also reverses. But the problem is the diode is going to be in reversed position. So if the current is coming from here, so the positive charges are coming from here, but this part of the diode is going to be only accepting the negative charges. So R1 would not be getting any, the circuit would not be complete, or this part of the circuit is not going to be complete. So R1 is going to have zero current. We can just write 0 current, and that's because the diode is going to be in reverse position. The diode is in reverse position. Determine the new value of the ratio of PD across R2 and R3. So once the cells are reversed, the diode would not be, current would not be passing through the diode. That means this is going to get, R2 is going to get 1. The current passes through R2 once, and it also passes through R3 only once. So that means the new ratio is going to be 1 to 1. So we can just write 1 to 1. That's going to be the ratio. Question 9a. Table 9.1 shows some properties and values of alpha particles, beta particles, and gamma radiations. Complete table 9.1. Okay. So the number of neutrons for alpha particles. So the number of neutrons for an alpha particles is going to be 2, because we know that if you write alpha particles, the mass number is going to be 4 and the proton number is going to be 2. So it has 2 protons and 2 neutrons. And for the beta particles, number of protons, they have 0 number of protons. And the charge is going to be negative 1.6 times 10 to the power of 19, negative 19. And for the gamma rays, the number of neutrons, they have 0 number of neutrons, and they have a charge of 0. And they are stopped by, so they can travel long distances, so gamma rays are only stopped by lead. This is because that gamma particles have low ionization, so they can travel longer. And lead, only thick lead is, or concrete is able to stop them. State how beta decay changes the nucleus of an atom. So what happens in a beta decay is that if we have a nucleus N and it has a mass number of M and proton number of Z, so during a beta decay, one of the neutrons is going to be removed and it's going to be changed into a proton and an electron. So the mass number increases by 1 and the number of neutrons decreases by 1. So it would be the neutrons would be decreasing by 1. So they have 1 less neutron and 1 more proton. So 1 less neutron and 1 more proton. C. A radiation detector used in laboratory detects a background count rate of 30 counts per minute. A radioactive source is placed in front of the radiation detector. The initial reading on the detector is 550 counts per minute. The half-life of the source is 25 minutes. Calculate the expected reading on the detector after 75 minutes. So the background radiation is 30 counts per minute, so we have to do 550 minus 30, which would give us 520. So the count rate of the radioactive source only is 520. And it has a half-life of 25 minutes. So the first 25 minutes, it's going to decrease to 520 divided by 2. 260. So the first 25 minutes, 260. It becomes 260. Now the second 25 minutes, or after 50 minutes, it also halves, so it's going to be 130. And the third 25 minutes, or after 75 minutes, it's also going to half again and become 65. So what's going to happen is, so it's going to be 65. So that after 75 minutes, it's going to have a count rate of 65 counts per minute. Part D. State 2 safety precautions taken when moving, using, or storing radioactive resources in a laboratory. So one of the safety precautions is going to be using a lead-lined box. Using lead-lined box. And the second one could be limiting the time of exposure. So limiting time of exposure. Those are one of the 2 methods. Number 10. I think this is the last question. A. State the equation that defines the average orbital speed v of a planet. State the meaning of any symbols you use. So the average orbital speed. So the speed v is going to be 2 pi r over time. So 2 pi r represents the circumference of the orbit. So let's say there's a planet over here, and we have an orbit of the planet. So that means r represents the distance from the center of the planet to the outermost orbit. So this is represented by r, and 2 pi r represents the whole distance of this orbit. So since we know that speed is equals to distance over time, so the distance is represented by 2 pi r, the whole circular distance or the circumference of the orbit. So this is our formula. Speed equals to 2 pi r over time. Suggest why countries that are a significant distance from the equator experience a significant temperature variation throughout the year. So one of the explanations for this could be that we know that the parts of the Earth away from the equator, they tilt, and when the Earth is rotating, the light or the sun hits those parts differently or at different angles. So we can write the sun strike the country or those parts, so the sun strike the country at different angle. At different angle. Part C. Fill in the gaps in the paragraph about a star much more massive than the sun. So now we know we're talking about huge stars. The stage that follows the stable star in the life cycle of the star is the dash stage. So after a stable star, what forms is going to be a red supergiant. If we were talking about the sun, it would just be a giant. Just red giant. But then now, since it's a star much bigger than the sun, is going to be red supergiant. So red supergiant. It then explodes as a supernova to form a nebula. So you need to have a good knowledge of the life cycle of a star. And then after that, this leaves behind a dash and dash. So it's going to be a neutron star. Neutron star. Or a black hole. If you want me to do a whole video on the life cycle of a star, make sure to drop it down in the comments. Part D. A galaxy is moving away from the Earth with a speed of 33,000 kilometers per second. The value of the Hubble constant is 2.2 times 10 to the power of negative 18 per second. Give the distance from the galaxy to the Earth. Give your answers in light years. So we know that Hubble's constant, or HO, is equals to the speed over the distance. We can rearrange the formula so that distance becomes speed over Hubble's constant. So now we have the distance, which is 33,000. And then we divide it by Hubble's constant, which is going to be 2.2 times 10 to the power of negative 18. Now we know that this distance is given in kilometers per second, so we have to multiply it by 1000 to get it in meters per second. So now we just divide that 33 1000 times 1000 divided by 2.2 times 10 to the power of negative 18. And then that would give us 1.5 times 10 to the power of 25 times 10 to the power of 25. But this distance is in meters, but then we have to convert it into light years. So we can just divide by, we know that 1 light year is going to be 9.5 times 10 to the power of 15. So we just divide this by 9.5 times 10 to the power of 15. So just divide it by 9.5 times 10 to the power of 15. And then we should get somewhere near 1.6 billion. So we can just write it as 1.6 times 10 to the power of 9. So this is going to be our answer. So that was the last question. And this is the end of our video. So if you enjoy the content, make sure to like and subscribe. And if you have any comments or suggestions, make sure to drop them down below in the comment. And thank you for watching.